Hello students, welcome to this lecture in which we're going to talk about double integrals in cylindrical coordinates. So what the idea is, sometimes it's easy to express functions in polar form. So it is sometimes easier express functions and boundaries in polar form. So basically that means cylindrical coordinates. Rather than rectangular. So how are we going to do that? First of all, what do we need to compute? What do we need to compute? That's the first question. So basically we need a generic little chunk of volume. So how does it look in picture? It looks something like this. Okay, so we have some area on the bottom, right? So if we go and move up to the surface, right, z equals to f, then this would be our little chunk of volume, right? So basically delta v, chunk of volume, will be f of r star theta star, basically a point, right? Basically some point in this area, times, so we take the point, we calculate the height, we have the height, and so we multiply it by the area of the bottom, right? The area of the bottom, so times area of this chunk of on the bottom. And if we can find this generic piece of volume, then we're gonna add them up, right? So we can calculate double sum over f r star theta star, and again we're in polar coordinates, so only r and theta, times the area of this chunk on the bottom. And for each such chunk, we're going to add up all of these volumes. And if we can calculate the double sum, then we can take limit, right? We can take limits. So what our limits would be as delta r goes to 0 and delta theta goes to 0 to get the volume. But if we think about this quantity over here is just tells you that the magnitude of the partition goes to 0. All right. Unfortunately, there are some complications with this idea which we have to overcome. So first warning is the volume is not that easy to calculate. So the volume is not just double integral, unfortunately, of f of r theta dr d theta, unfortunately. Why is that? Because the chunks that we have, the little chunks that we're talking about are not, let me say it correctly, the little chunks of area in the xy plane are not rectangles. Why? Because in polar coordinates, what you're going to get if you think about delta r and delta theta, you have an array going like this. So that means your delta theta is the angle. Delta theta is this angle over here. This is your delta theta. All right, and if you think about delta r, you're going to be moving along the ray. So you're going to be moving like this along the ray. So this will be your delta r that goes from A to B along the ray. So that's the area that you want to calculate then for this strange chunk. So basically, if you zoom on it, you have something like this. And this is the area of this chunk. All right. So unfortunately, you can't just use this as your volume. So basically, this chunk, they are sections. They are sections of circles. Sections of circles. So chunk looks like this. So the question is, how do we compute the area of this chunk? So how do we compute the area? Maybe that area, right? So let's go back to calculus 2. So we have to recall that if you have a sector with angle theta and radius r, and its area its area is theta over 2r squared. So what is the area of a chunk? Area of a chunk is equal to delta theta over 2 times r plus delta r squared. All right, minus delta r over 2 times r squared. So basically, visually we do the following. If this is your delta theta, and you can take the area of the bigger piece in red and subtract the area of a smaller piece in blue, and you will get this chunk by taking the difference between the area of the bigger sector and smaller sector. All right. So if we keep calculating it, if we keep moving forward, then we're going to get delta theta over 2, and then we have r squared 2r delta r plus delta r squared if we take this and square it, and then we have r squared at the end. But the first step I did, I factored the common factor. So if we keep calculating it, calculating it, we see that this r squared and this r squared adds up to 0, and if we multiply by half, we're going to get r, 2 will disappear, this 2 and this 2 will go away, so we'll have r times delta r plus delta r squared over 2 delta t at the end. I moved delta t to the end. So we calculated the area. Now we can move to the volume. So we can say the volume is the limit, like we agreed. Delta r goes to 0. Delta theta goes to 0. We have a double sum, and we have r delta r, and we can move delta theta inside because later on I would like to split this to integrals. Then we have delta r over 2, and we have delta r delta theta. So I took this delta r squared and I wrote it as delta r times delta r, so I'll have this delta r delta theta, delta r delta theta. And we need to multiply by the function evaluated at some point of your choice. Alright, so we have a limit. Again, delta r goes to 0, delta theta goes to 0, and we split this into two sums. First sum is r delta theta times f r star theta star plus the sum, actually double sum of the second part, delta r over 2 delta r delta theta f of r star theta star. So finally we have, not finally, but next step we have limit delta r goes to 0, delta theta goes to 0. We have a sum f r star theta star. If we move it up front, then we have r, we have delta r, we have delta theta, and this is a good setup. We have some kind of a function times delta r delta theta. We have a double sum. This is pretty close to the definition of the integral. And the same for the second one, limit delta r delta theta both go to 0. A lot of times people write it through the comma, but it's fine. So we have sum, we have double sum, and we have f of r star theta star, and we have delta r over 2 delta r delta theta. All right, so basically this one is all set, this one is all set. So basically this is a double integral over area f of r theta r, because we can think of this as our function, and this is a chunk of area. So we get dr d theta for this integral. For the second one, it's not that easy. We can just take a integral with respect to theta first, because as you remember, it doesn't matter in which order we take limit here. So we have still delta r goes to 0, but then we use the integration. So it's going to be the integral f of r star theta star, not theta star, but theta, fixed theta, delta r over 2 delta r, but now delta theta becomes d theta. But what happens over here? So since we fixed our delta, since we fixed theta and theta doesn't move, that means we move along one line, right? So since theta will not be moving, so it's we're going to stay on one line, but the area under one line, area on the line is just 0, right? Because we don't really move from it. So that means this whole chunk is just 0. So that means we only have first piece that gives us some value. Conclusion, the volume is equal to double integral over area f of r theta times r dr d theta. All right, so there is a simpler case. So in a simple case, our volume is the integral from theta 1 to theta 2, r1 to r2, f of r theta times r dr d theta. All right. Okay, so we're ready to do an example just to see how it's working out. The first example we're going to do is this one. The assignment says evaluate double integral over the region R, sine of theta dA, where the region R is the first quadrant that is outside the circle of radius 2 and inside the cardioid, r equals 2 times 1 plus cosine theta. All right. So let's try to imagine what it is. I used WX maxima to do that. So basically we load the draw package, then we say the coordinates, we put the color blue for the cardioid, and we put the color red on the circle. So if we do that, we get this picture, and maybe we can say WX draw. This way we can take it and copy it. All right. So, all right. We have this kind of a picture. Okay. So what do they want us to do? They want us to calculate the area inside of the first quadrant, right? So we would like to stay in first quadrant. So we'd like to stay over here. Okay. So this is X, this is Y, and we would like to stay inside of one quadrant, and it has to be outside of the circle but inside of the cardioid. So between the red and the blue, but only within the first quadrant, So basically this area over here. All right, so this is our theta equal to 0 here. This is our theta equals to pi over 2. All right, and the radius of a red circle is r equals 2. Now we need to find the radius of the blue cardioid. So the radius of the blue cardioid is this distance over here, and this point is given by r equals 2 times 1 plus cosine of theta. Okay, so we're ready to set up our integral. So our integral will go over the region sine of theta d theta. So for the angle we have 0 to pi over 2, and for the radius we have 2 to 2, 1 plus cosine of theta. Of sine of theta, that's our function, times the r, because it has to be, as you remember, r over here, and we have dr d theta. So let's try to calculate this integral over here. So we keep the outside, but we calculate the integral in terms of r. So sine of theta stays, and the antiderivative of r is r squared over 2. That's antiderivative of r, right? And then we still have sine of theta, and we evaluate it for r from 2 to 2 times 1 plus cosine of theta. All right. And I forgot one more thing, which is d theta. So let's move forward. So we evaluate, we plug in 2 times 1 plus cosine of theta. So it's going to be the integral from 0 to pi over 2. Alright, so we're going to get 4 1 plus cosine of theta squared divided by 2 times sine of theta minus, we plug in 2, so it's going to be 4 over 2 sine of theta. And we put brackets, and we have still d theta at the end. So as you can see, this 2 and this 2 and this we can divide, and we have 2 as a common factor, so we can put it outside, and we have integral from 0 to pi over 2 we have 1 plus cosine of theta quantity squared sine of theta minus sine of theta d theta. So this integral over here is really easy to calculate. It's just going to be antiderivative of negative sine is cosine of theta. And over here, we would have to calculate the integral. Let's do it on the side. The integral from 0, the antiderivative. Let's find the antiderivative. So indefinite integral of 1 plus cosine of theta squared sine of theta d theta for this part. So the change of variable u equals to 1 plus cosine of theta gives us that differential of u is negative sine of theta d theta, and that means that du over negative sine of theta. So if we plug everything in, we're going to get u squared sine of theta du over negative sine of theta. So finally we have the minus, and antiderivative of u squared is u cubed over 3, and u was 1 plus cosine of theta, so it's minus 1 plus cosine of theta cubed divided by 3. Alright, so I'll erase this part. So now we continue with our integral. We say 2, then we put a bracket and we put this term first. So it's negative 1 plus cosine of theta cubed over 3. And we have antiderivative of negative sine is cosine, so let's put plus cosine of theta evaluated from 0 to pi over 2. So we have 2, then we plug in pi over 2, cosine of pi over 2 is 0, so it's negative 1/3, and this is 0, and we have minus, and then we plug in 0, but cosine of 0 is 1, so we have 1 plus 1, so it's going to be what, 2, right? So it's going to be negative 2 cubed, so it's negative 8 over 3, and then we plug in 0 into cosine, we're going to get 1. All right. So what do we get? So instead of 1, we can think of it as 3 over 3, so it's negative 5 over 3, so it's positive 5 over 3, so it's going to be 4 over 3 times 2, so it's 8 over 3. And that's our answer. The area will be, the volume will be 8 over 3. Okay, so again, our assignment was to evaluate this integral, and we did this out. All right, so probably a good place to stop the discussion here. All right, and I'll see you in the next lecture.